You know what I mean? As a teacher, it's hard not to feel like.
I am currently doing that. To reality.
It's not your fault.
Can't shoot.
It kind of feels like it though.
Okay. Shoot it.
Oh,
shoot it.
yeah,
Shoot it.
yeah.
Shoot, Mark. Shoot. Right there. Right there. Can I take this desk apart? I need Lars.
Getting the small ones finished. Really good.
Can I take Lars? It'll keep me up.
No, come on. Let's go here. We don't have a whole bunch of time. Okay. So, we know that gas particles are in rapid random motion, and they're going to collide with things. And when you have an object that's moving, and it runs into something, it's going to apply a what?
Pressure.
A force, which over an area will produce a pressure. So in theory, guys, right now we have a whole bunch of air particles that are colliding with our face at this very moment, kind of like saliva falling into your eye.
Stop.
Just keep saying. Can't you create pressure with your mouth?
Just and so even though one air even though one air molecule colliding into your face isn't going to exert much pressure because it's such a small particle, if you start taking the millions and millions of particles that are all colliding into your face at the same time, it's going to exert a decent amount of pressure. Okay? So we need to define what pressure is, which is a force over an area. This is kind of elusive. This is not supposed to be a little, that's not a negative. Okay? A pressure is a force over an area. Okay? So,
we talked about
Stilettos used to be like squishy.
what?
you have
Like,
like,
it's just there wasn't a
like
force on our face.
something lifting you up, right? Wait, so could you have a negative pressure? Like somebody like pushing you up? Is that like?
That's just pressure from the inside.
No. That'd just be a different force of, different. Okay, so
You're right.
if I take a step and I step on someone's toe,
Nice.
okay? I'm exerting a force over an area.
Small area.
Okay, exerting a certain pressure on someone's foot, okay, versus taking high heels and coming over here and going wham, right on someone's foot. Why would the high heeled situation hurt more?
Because it's a smaller area, but you have to exert the same amount of force.
Okay, so what you would have is the same force, assuming you had the same person stepping on you, because it would be the same weight of that person. Same force, but over a smaller area, and so it's a much higher pressure. So don't, going out in your high heels and walking on ice.
Do you know what
I will not.
What?
Do you know what stilettos are?
Pumps?
Well, what if,
Stilettos are burger. They have like little
but you're,
spikes.
okay, but you have the same amount of weight on your foot, even though,
But
Yeah,
it's like a
technically,
smaller area.
yeah.
No, not.
so you're saying if you just use your heel,
Yes.
but if you use like your whole foot, it'd still be the same.
But-
No, it would be a little less. Like
It's
if I use
still
my whole
more
foot
even
versus
though
your whole
you're
foot,
half-
you have less area of your whole
Like
foot.
if you
than I
walk
would,
on your
because
whole
you
foot
don't
all
have
day, it's
this
gonna
much.
What
less pressure than
What
just
if you're
walking
wearing
your
like
foot.
wedges, where they're like heels, but it's all the way
Then that
across?
probably wouldn't change much.
No, but now
Okay.
like.
Hey, guess what?
Nail.
You see this right here? You're gonna have to memorize this, along with quite a few other things.
What the heck is all that?
1 atom equals
600
meters.
660
That's not
millimeters.
Sure, I've seen that video.
What video?
Speaking of pressure, this guy hot glued tacks to the bottom of his shoe, took a bunch of them, filled the whole bottom of his shoe, and then just he gave his friend a kick in the stomach with it. They're so stupid.
What happened?
Pressure, little tiny nails, the force.
I don't think it has anything to do with that as much as the pressure as it has to do with their sharp objects, and that probably.
Well, sharp objects.
Yeah, it's a result of pressure change.
I was
What
trying to
happens
put
if
that
what happens
in
if
there.
your stomach is punctured? Or like your
Why?
skin is like, does it like
What
release
is
all
the
the pressure
point?
in your stomach and you die or what? Like if they're like do acupuncture on your stomach.
Well, I'm pretty sure that wouldn't kill you, because if it would, they would not be doing it.
Because This isn't there, no, I'm talking, like, isn't there
No,
pressure
don't
in your
do that.
stomach? Like, you're.
I don't know what that has to do with chemistry, so I don't know. Yeah, I'm not sure. I mean, if someone took a knife and slit your stomach open, then yeah, you'd probably die.
I'm sorry, I don't know.
But I don't think it's because of the pressure differences. Alright, so can I explain this?
You can.
Okay? First of all, the SI unit, or the most common unit that we're going to use for pressure, is called a Pascal. Okay? So you're probably wondering, what in the world is this, Mr. Kramer? Okay. Let me show you something that may help you understand this. So let's say I've got
Oh God, oh God.
a kilopascal.
Kilo, thank you.
That's funny.
It's a
A
Okay, it sounds like an
Does
indeterminate.
that little visual that I just showed you help you understand what the top is trying to tell you?
What denomination?
Does that not help you at all?
I don't understand,
I know you don't understand what those units are up there, but do you understand what the bottom units are?
yeah.
Yeah.
All of those numbers equal each other.
Should I write that down?
No, not what I wrote in.
Okay.
No, that makes sense, yeah.
Oh, well,
Okay,
yeah, I already
so
know.
what this is supposed to show you is, here are all your different types of pressure units.
Oh.
And this is how all of them equal each other. So, you're gonna need to know this so that you can do pressure conversions.
Why are there 2 stars now?
Whoa.
So, let's do our pressure conversions.
I wonder so.
Hey, you guys remember chapter 3 when I made you do unit conversions, and then we used it in stoichiometry where we did the same process of using unit conversions?
Yeah.
Hey, it's coming up again. I can't believe you guys don't remember how to do regular unit conversions. That drives me nuts if you guys don't remember that.
I remember it, I still want to do it.
Okay,
It's not a unique number, like 6 foot.
okay, so convert 1.20 atmospheres, that's a pressure unit. Okay? And we want to convert that to torr and PSI. So we're gonna set up a unit conversion. When you do a unit conversion, what you're doing is taking 2 equivalent units and putting it into your conversion. Hence, the focus on equivalent units. Like if I want to convert feet to inches, in my conversion factor, I better have how feet equals inches.
Right.
That make sense?
Is
If
the
I
one
want to convert atmospheres to torr, I better put in the equivalence of those 2 things. How many atmospheres equals how many torr? Okay? So, that's where that big long expression is what you need. Now, from a unit standpoint, how would I get rid of this unit?
On the
One
bottom.
makes on the bottom.
Okay, and I want to convert to torr, so that's going on top. And what is the expression that makes those equals?
760.
760 torr is equivalent to 1 atmosphere. So if I have more than 1 atmosphere, I better have more than 760 torr, correct?
Right.
Very similar to what we did in chapter 3. Very similar to what we did last chapter. Why is this important? Well, some particular gas laws need a specific pressure unit. Which if you're not given that specific pressure unit, you need to figure out how you're going to get that pressure unit. I don't hear any calculators tapping away.
I said when you said that.
What?
912.
I want you guys to do the second one. The PSI. I want everybody else to solve for how much PSI that is.
Big number, big number.
That's about to be big.
No. Not really.
It's not going to be that big. PSI?
That's like a year old.
Oh yeah, just kidding, move
You guys know what PSI stands for?
Pressure
per inch.
Okay.
Pounds per square inch.
So close.
It is a pressure unit,
Yeah.
but
Oh.
it's actually what we use in America. Your tires, it's
Do
a
these really
PSI.
sick things?
Yeah,
That is a big number, come on.
not as big as this number.
Oh. But it's still,
What's big to
I
you?
think age-wise.
A year older than us.
Wow,
Okay,
17's
number.
so big.
Gosh,
17.
really old then.
If you really look at it, I mean, there are an infinite amount of numbers between 0 and 0.1.
Gage, stop.
Really?
Alright, so what'd you guys get?
That's 17.
17.6. Did you guys start with 1.20 ATMs?
Yeah.
Yeah.
Okay, let me show you another way to do it.
But you can also go.
Oh, no.
Or.
But why?
760 torr and 14.7, right?
That makes it harder.
Seven.
And if you were to do that, you should also get the very same PSI number, which is 17.6.
That's what I did.
Okay? Pretty cool. All those things equal each other. You could really you could convert any pressure unit to any pressure unit, any variety of ways you find fancy. Okay. Just to make sure, do these two quickly. Because Pascal is your SI unit, so I want to get that. Does anybody know what MMHG stands for?
Millimeter.
Yes. Pretty good. Millimeters of
Trinity
mercury.
said first, but I.
Millimeters of mercury is what is used
Thank you
in
for that
barometric
nice-
pressure barometers.
What's that called?
We'll talk about barometers, I think, in this class.
No,
Acknowledgement?
what is that? You're giving me the credit. Thank you for giving me the credit. That's
Give
the
me the
word.
glory. All the glory.
Society resources.
Yeah. Wow, that's a big number.
This is gonna be a big one, I was about to say.
What? To write it in the blank is big.
But did you know that every number is a big number? That it has an
Every
infinite
number.
number of numbers in between the numbers?
Okay, well, if you look at it that way.
Okay. You remind me of John Searcy.
I think you told him that last year.
I don't remember
Because of the just random things that would come out of it.
Yeah, you
And if
said
you
one
want
time
to
he was
get
talking about
digits, you want
jelly
what
or
you're given.
something like
What?
that.
Oh, yeah, I
better
did
get
say
digits,
that.
you want what you're given.
Yep.
You weren't in our class, Trinity.
No, he said it in chemistry. It was not
I
past.
think I did say it.
He was saying it like last semester.
That felt like it was last year.
It really does.
Hey, what is the atmosphere number?
Oh, I have
It ends up being, due to sig figs, the same number rounded,
Yeah, that's what I'm saying.
which even though we know it's not 760, it was 790, but because of sig figs, it ends up rounding to the exact same number. What about our Pascal number?
110.
110,000.
Same thing.
What?
What?
Wait.
Or, yeah.
That's
what
what
I
I
have.
did.
Did you use kilopascals or pascals?
That's Kelly's.
The 101, 325?
Yeah. 790 times 101. Oh, it's 10. I did 3.325. That would be kilometers.
Did I get that?
No, I did 790 times 101,325, and I got 80 million.
How?
Did you divide by 760?
Oh, I'm dumb.
Oh, dang it.
Woo-hoo!
Oh yeah.
Oh my goodness.
There it is.
Oh my, wow. Yeah.
Nice, guys.
Like that?
Woo!
Conversion factors.
That makes sense?
Woo-hoo!
Are you having that much fun over there?
Woohoo!
I just realized,
Using a fraction.
What in the world is that thing?
Wait, you.
Oh, you still have it?
And this is just what it is.
I thought you got rid of it.
That's great. I'll
It's
take it.
usually like an S to D. That thing's like,
Ancient.
yeah.
Like, first,
I brought it at the beginning of the year, and
I
then I got a
know,
new cafe.
I almost want to like pay you for that.
You
so
told
like-
her that earlier.
Did I?
Yeah, but last
Okay, that makes
semester.
sense. That thing is
Me.
like almost as old as me, probably.
Probably. Pretty old.
I have
This
this.
is my buddy.
It's so random. Sorry, Mr. Marvin. I don't want to say it.
Alright, first gas law.
Why do birds
Hey, everybody turn to this page.
Whoa.
We will do 6 laws over the course of this chapter,
Great.
and you will have to memorize all 6 laws.
I do not like it.
This exact graph, listen, you might want to listen to this,
It's on your test.
is on your test.
Oh my.
Oh, fart.
And you'll have to fill it in.
That's actually.
Oh, fart.
So it's like 18 freebie points if you just know it.
It's not pretty because you have to memorize it.
But we're using so much that it won't be too difficult. Okay? So, your first thing that you are going to put in there, your law. You will put in Boyle's law in the very first blank. Then it says, what is your equation? You will put in this equation. It's not a negative, that's the equation. Then, your constants are going to be temperature and moles. And you can abbreviate moles with N if you want, because that's the variable symbol for moles.
Capital.
Lowercase then.
What's the other name?
I will explain.
The constant?
Yeah, that's a constant.
So,
Which I'll explain what this comes from this.
so what should this look like?
Wait,
In the
where-
constant, you should have temperature and moles are your 2
Yeah.
constants. I can't. Is that what
Sorry,
you wrote?
is that capital or not?
Yes. Yep.
Okay,
Now, let me
so-
show you.
Oh wait, when it says law, you don't want like what the law is, you want the name of the
The
law.
law is the name. Yeah, put the
Okay.
name in for the law.
Okay.
The equation is the one that I have boxed down there. That's the one we're going to use. The top equation is where we get the bottom equation. So you don't have to use the top equation. I'm just going to use it for clarifying how they came up with the bottom equation. Okay? So Mr. Boyle, what he did is he did all, I'm not going to get into all the experiments that he did, but he figured out, discovered that volume is inversely proportional to the temperature, or sorry, to the pressure, as long as your temperature and your moles are held constant.
Oh.
Okay? So what he said was, if you're, what is inversely proportional?
One goes up, the other goes down.
One goes up, the other goes down. So if you increase the pressure,
On the external force.
Volume
internal
goes
force.
down.
that-
You, on a container, if you increase the external, the internal goes down.
yeah. Okay?
That's the whole question.
Or you could also, wait a second. Yeah, you have to. Okay? Now, the reason why temperature needs to be held constant is because if you change the temperature, that's going to change. We're going to figure out how the temperature is going to affect pressure. We're going to figure out how the temperature is going to affect the volume. And so what they did is they isolated 2 variables so they could see specifically how they impact each other. Okay? Now, what this is saying is that for any gas, under ideal conditions, if you increase the pressure, the volume goes down proportionally. Or if you decrease the pressure, the volume goes up proportionally. No matter what, it gives you the same number. So if my pressure is 4 and my volume is 8, I get 32. If I decrease my pressure to 2, my volume goes up to 16 to give you a constant. Well, if that's true, then I could have P1 V1 equals constant. I could have my second situation, P2 V2, would also equal the same constant. And so what do you think they did to get this? Replace K with K, since they are the same. So what this is saying is, if I know the initial conditions, okay, and the final pressure or the final volume, I can find the other variable, and vice versa.
Wait, so what is K? Is that the,
It's just a constant, I don't know. It just will always be the same for every gas.
so this gas is 32.
Yeah,
32 what?
it's a unit, what's number? It's a constant. It just shows you that it's a perfectly linear relationship.
Find it then.
Experience.
Natalie, don't you want to put
You just say this gas is 12.
Well, you're talking about the fact that it doesn't have a unit?
Yeah.
Yeah,
Can you say that?
pretty much.
So to find it, you just have to find the pressure, the volume first, and that's
For a
the
specific gas,
constant.
yep,
And then work on that.
yep, yes.
So if you have a perfect. Don't say
Say it. She's done.
I got two problems to go through.
If you
here.
have a perfectly linear relationship, that means it's true.
Straight line, yes.
Wow.
Okay,
Take that, YouTube.
here you go.
Amen.
So here you can see, I'm increasing the pressure, which is causing the volume to do what?
Decrease.
Decrease.
Whoa.
Everybody see it, an inverse relationship. You could also say that if the pressure decreases, the volume's going to increase so that you maintain the pressure outside and inside. Okay, now you can imagine why temperature needs to be held constant, because if these particles are moving faster, won't they exert a greater pressure?
Yeah.
Yes, I'm gonna do one problem, don't leave. The second one's very similar to the first one here. Okay, a sample of gas occupies 450 liters under a certain pressure. If the volume of the gas is changed or increased to 550 liters, what will the pressure be? We must label P1, V1, P2, V2. What's V1?
First volume. Second.
What's P1?
3 to 18.
Be careful with this. Sometimes it's not always the first two numbers that go together. Read the context of the problem. Okay? Then it says, what will the pressure be if you increase the volume?
That's a nice question.
Now, if you're increasing the volume, what has to be true about the
It's
pressure?
gonna go down.
It's going to have to go down. So P1, V1 equals P2, V2. You will plug in, and you will solve for P2 by dividing by V2.
Where are you hiding the dump?
Okay? Hold on, guys.
Hold your horses.
Okay? So you can take your P1 times your V1, divide by your V2, and you should get
07 plus 18.
Yeah, you're right. You're right. Same things.
Wait, aren't you solving for?
Solve for pressure.
Oh yeah, I just wrote
1.8. What did I say? 1.1 atmospheres is your answer?
Wait.
I don't find this math to be overly difficult. I don't feel so bad if we didn't get to the second.